Morning, calculus.
Morning.
Day to you all.
Morning.
All right, let's get after it. Sharing the screen. Turn off the radio. So Cheyenne found this. I mentioned the other day about extra credit regarding history. I just thought you might find this interesting because I did. And since you're here on time, let's learn something. So the Maclaurin series, named after or created by, but here it says named after Colin Maclaurin. Look at this dude. Look at that hair. Very interesting though. Just on a side note, child prodigy. He started attending the university at age 11, and he became a professor at 19 years old. And he held the record for being the world's youngest professor until 2008. Isn't that crazy? Somebody beat him recently. That's insane. Anyway, all kinds of, I don't know, interesting stuff. Good find, Cheyenne. That was awesome. I didn't click on any of the links, but I also thought it was kind of cool as he was known for being a good teacher. That's kind of neat. That's not typical for somebody who's really sharp. Usually they're don't understand why everyone else around them is so dumb. So thanks for finding that, Cheyenne.
Yeah, no problem.
Let's see. I got a lot of stuff to show you today. How are we going to get through it all? Let's get after it. Let's start with that. There's one problem in your assignment from yesterday. I'm tempted to start with that, but there's some things I want to show you about 11.4 first, and maybe we'll get back to that if we have time, because there is a video in the homework assignment in 11.3 about it. So I still want to talk about it, I'm hoping. But anyway, let's kind of talk about 11.4, which is still dealing with, and the title in the book is almost the same, still dealing with the concept of a Taylor series. And I'm definitely going to ask this kind of stuff on a test, but what really this comes down to is kind of like, let's use these notes. In other words, let's see, did I already bring this in? In other words, using this page. In other words, let's not recreate these again. Let's use them. And I want to show you one example of that right now. So let's use these common Taylor series expansions to, I don't know, get some other work done. So let's stare at this one, for instance. And again, notice that's fairly cool and simple. We made that. I think we made that. Yeah, we did. So it's really x to the 0 over 1 0 factorial plus x to the 1 over 1 factorial plus x to the 2 over 2 factorial. So E is kind of a neat one. It's if you had to memorize it, which you don't, but if you had to, it wouldn't be terrible to do so. But application. This is one of the reasons this was invented, and one of the reasons this starts to be really cool. So last term in calculus, I showed you the normal curve. We did this for a project, and if you had some stats, it made a little bit of sense to you, but that normal curves equation is, and I've it memorized, I'm staring at it over here, 1 over 2 times the square root of pi times e raised to the -1/2 x squared power. And so that creates this normal curve that you've all kind of seen, sort of a bell curve. It's not too bad of a drawing right there. And the area under there equals 1, or a better way to think of it is like 100%. And so, and notice this is centered at 0. right now. And so this is used for all kinds of things in statistics, even if you haven't taken statistics. Like if you're the person ordering shoes for a company, how many shoes of each size should you order? Well, you need to know what the average shoe size is. Maybe that average shoe size was, say, a 10 or something like that. And this tells you what percent of your shoes you should order kind of in each size. And then obviously it naturally would get less and less as you get really small, and less as you get really large. But this just has all kinds of practical applications. And it's really the area under that curve. And so in order to find it, as you remember from Calc 2, the area under curve, you got to take the integral of that. And so last term, we said, well, you can't take the integral of e to something so complicated because of chain rule. Unfortunately, that's not as simple as, oh, the derivative or the integral of e to the junk is e to the junk, because that junk is complicated. If you try to make a substitution up there so that becomes e to the u, your substitution is messy. That is not, you can't really even do that. You can't find the integral of that. I want to say can't with quotes because I can't remember how deeply I've looked into that. So very difficult integral to take, if not impossible, so that you can find the area. As a quick reminder, because we're going to do this in just a second, if you go, as mathematicians describe it, one standard deviation above and below this, one typical deviation above and below this, that area right there is 68%. So 68% are within one typical or standard deviation of the mean. Again, if you've had stats, it probably speaks to you. If not, you're probably going, what are you talking about? But suffice it to say, let's try to, well, find that area right there. Supposedly that area is 68%. And we did that using Simpson's rule. We said, well, we can't take the integral. So Simpson's rule was a cool numerical trick to find a ridiculously close approximation of the answer. And we used Excel to do that. Well, now let's use what we just learned. So let's consider for a second this statement. So what I would like you to think about for a second is, if you replaced, let me see, is the 1/2 part of the squared? I think all of a sudden I'm spazzing out thinking I can't remember if the 1/2 is part of the squared or not. I don't think it is. I'll look it up while we're playing. The question is, we just saw a second ago that e to the x has a power series expansion. We don't make it again from scratch. We're just cheating. And on the test, I'll say make this from scratch for some problems. And others, I'll say use the note sheet. Well, the note sheet said this is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so forth. Well, all you have to do is replace x with, well, what x is equal to here. So the question is, could you use that fact to write the power series expansion for that? I'm going to double check real quick and make sure that the 1/2 is not being squared on the internet while you were at least getting a head start on that. I'm pretty sure it's not, but yeah, it's not. This is really easy. You're just replacing it with x. You're replacing x with that. So, okay, well, the 1's a 1, so that's fine, plus, well, x. But what is x? X is negative 1/2 x squared. There's x. And plus x again, except for this time x is squared divided by 2 factorial. And then plus x again, except for it's cubed divided by 3 factorial. And we'll quit right there. Let's just quit with 3. We'll say we'll model this with a cubic for now and say we're done, except for, you know, what is our x? Well, it's negative 1/2 x squared. And so you're done. Like, that's the expansion, except for, you know, if you're going to use it and so forth, you might find yourself wanting to kind of clean that up a little bit. So let's see what happens to that. Then So again, in the language of your book anyway, you might call this P3, which really just means polynomial degree 3. So it has 4 terms. I'm going to quit with that. Okay, fine. So this is 1 and then minus 1/2 x squared. But then notice the next time it's squared. So let's see, what does that actually equal? I guess that'd be 1/4 x to the 4th. But then the 4 on the bottom is multiplied by 2 factorial. So you have 4 times 2, you have 8. And then the negative 1/2 turns into a positive. So don't you get 1/8 x to the 4th? If you simplify that. Let's see, and then 1/2 cubed, negative 1/2 cubed is negative 1/8, but then 3 factorial is 6. So you have 1/8/6, that's 1/48. So this is 1/48. And then x squared cubed would be x to the 6th. And so there's a nicer looking expansion. Now, again, why are we doing this? Well, because we're saying if that's a model for this equation, in other words, if I can just replace this nastiness with this, isn't that an easy integral to take? In other words, if a person is saying, I would like to know what the area under this curve is, so this is the application part of this. The whole goal here was to find the area of 1/2 square root pi e to the negative 1/2 x squared from 1 to negative 1 to show that it's indeed approximately 68%. 68% of people fall inside 1 standard deviation. We're saying can't do that. Okay, well, could you do this instead? You may remember that 1/2 square root of pi being just a constant can come out front. The question is, could you just do this instead? Would you agree? Thanks to the fact that that's a polynomial, we do not mind taking derivatives and integrals of polynomials because they're so simple. Only rule we need is the power rule. Previous question right here. Not only is that ugly substitution, but it might not even be possible. Whereas this question, totally easy. So cool. Now we chose to stop at a 3rd degree polynomial for this, which notice it actually turned into a 6th degree polynomial. So that's kind of interesting. So that, the question would still remain, like, how accurate is this? Is this going to be good, or should I go a few more terms? And that's what the error business of this section is about. But let's just go ahead and finish and do this. This isn't hard at all. I can kind of do this by hand. 1/2 square root pi comes along for the ride. And when I take the integral of 1, I get x. When I take the integral of x squared, I add 1 cubed, then divide by 3. That becomes 1/6 x cubed. Raise x to the 4th to x to the 5th, divide by 5, and that 1/8 becomes 1/40th. And I raise 6 to the 7th power, and then I multiply 7 times 48. 7 times 48 is 336. So this last one is 1/336, x to the 7th. And then I just evaluate that at 1 and negative 1. And supposedly, according to statistics, we're supposed to get something around 0.68 for that. So let's see if we do. Let's see, 1 minus 1 divided by 6 times 1 cubed. Notice putting 1 in makes this really easy because I can just say, well, 1 to the 5th is 1. So it's really just 1 minus 1/6 plus 1/40th minus 1/36. 336. So I get 1/2 square root of pi times, and we're just getting an approximation here. So 0.88553. I'm just going to round it right there, 0.855. And then I go back and it's automatically subtraction. But what happens when I put negative 1 into this? What What's going to happen when I put -1 in? Notice all the exponents.
All the signs should flip.
All the signs are going to flip. So if that's the case, we're going to get the same exact answer except for negative, aren't we? I think I'm right about that. We'll find out in a second. And so I'm actually subtracting a negative, so that's actually adding it. So if I double that number and then divide by 2 square root pi, I get the wrong answer, 0.48. So 2 possibilities. I just did a lot of math. Could have made a mistake someplace. Kind of hope I did. The other possibility is this isn't a very big equation. I mean, it only had 3 terms in it or 4 terms in it. Maybe I should have gone further. Maybe it's just that inaccurate. So we're going to go look at the graph and investigate a little bit, but does anybody see anything wrong with it before we do that? I'm double checking myself here. I don't see anything wrong with it, so I'm thinking it's just an error. Either way, so let's go look at the graph in a second. And we'll see if it's an accuracy issue. But either way, isn't that kind of cool? I mean, that's why this was invented, if you will, or perhaps maybe I don't know that's exactly why, but at least that's a use for this that's really powerful, because you can turn anything into a polynomial now. Then if you need to do calculus for some reason, take a derivative or an integral, it suddenly makes things possible that weren't possible before. Again, this is the reason why the derivative of sine is cosine, which we kind of assumed earlier. So it takes crazy statements and allows us to answer them. Or, what's the derivative of natural log of x? You could now prove that that was 1 over x, because we could write a polynomial for the natural log of x and so forth. So that's kind of cool. So let's take a quick side journey here. Look at the graph. Which I was playing with right before class. So let's make this graph look a little better so you can see it more nicely. Let's see, I want the y to not be so far apart. So let's have the y be from 0 to 0.5. Okay, there's a picture of the actual normal distribution. And from last term, let's cheat really quick. If I rename this thing f of x, from last term, you may remember we said, what's the integral of this from -1 to 1? Let's see if this will do it. I can't remember if this will do it or not. Yeah, that tells me I actually have the formula written down wrong. That's not even the right formula. What's wrong with that formula? So notice we got the answer we were supposed to get, 0.48. But that means, because it's supposed to be, I just know it's supposed to be 0.68, which means I probably didn't even write the equation down correctly, which seems kind of dumb, but I thought I did. Doesn't take long. Let's just have a quick look. Normal curve equation. Huh, that's interesting. Well, let's leave it at this for now. Not go down this rabbit trail. So notice the actual answer to this equation is supposed to be 0.4827, but again, that's an integral we can't take. And so apparently Desmos is not doing calculus, it's doing this numerically, like using Simpson's rule or something from last term. And so we just got the same answer. We took the integral and got the same answer. Let's take a look at the curve that we just made and see how good of a fit it is. So we just found that equation right there as a mimic or as a model for it. And notice it's a really good fit between 1 and -1. Do you see how close it is? It's like, man, it isn't missing by much there. That's pretty darn good. So notice it isn't good if we went from -2 to 2. That's not good. If we would have went from 2 to -2, that wouldn't have been a very good answer. But it was awesome from 1 to -1. You don't need to know this, but it's just kind of fun. Take a look over here. If I replace this with a 3, that's the same graph. Just for the fun of it, this isn't super important to me, but I was talking with one of you after class yesterday. Michaela after class, she was just asking me questions about this a little bit more. But notice it's an alternating series, plus minus plus minus, and that happened because we had a negative number that was being raised to the first and then the second and then the third power, so it was alternating. So there's the alternating part of it. And then on the bottom, we always had a n factorial. That was a part of what e was, but then also that 1/2 was being squared and cubed. And notice we were taking that 2 and raising it to the first and the second and the third power. And then notice the exponents, because it was a squared equation that was then raised to another power. We didn't have every exponent. We had x to the 0 and x to the 2 and x to the 4 and x to the 6. And so again, notice the power of being able to write this way is now we could take this out to say one more term, really easy, and see like what would it take to model it to 2. So notice that's a 8th degree polynomial. And so the 8th degree polynomials are shaped like W's. And so notice it's not a good fit between 2 and -2 yet. It's an excellent fit between 1 and -1. But let's take it out to, I don't know, 6. Notice it's getting closer, 8. There we go. So now I could say, now I think we could find the answer between 2 and -2 and have a pretty darn good estimate. We just need more terms. And so does the concept of error make sense, and how it's kind of neat to graph it and sort of see how it compares to the original graph? And so, okay, well, that wouldn't be hard. It's just a larger polynomial. So that's what this is invented for, is finding approximations. And notice you have to approximate this. Like I can't put infinity up there for 8, but I can stick the minimum number of terms possible up there. So I have 9 terms. Since I started at 0 and went to 8, this would have 9 terms, but that makes an excellent approximation, at least from 2 to -2, close enough. Notice it shows us it'll be a little high because the green graph is a hair above the red graph. So I know the area under the green curve will be a little higher than the right answer. Just out of curiosity, because I don't know if it'll actually do this. Let's see if I rename this as g of x. Let's see if it will do it. And we wanted to know from 2, I wish I would have changed this before I copied it, from 2 to -2. Notice it's accurate to within 1, what is that, 10,000th? I mean, so it's, and notice it is indeed just a hair higher. The green graph is a hair higher. And so it got 0.6750 instead of 0.6749. So it is a hair higher, but again, an excellent estimate. Isn't that cool? I mean, this is the payoff of some of the things we've been studying. It models things that are really cool, really powerful. bothered by that wasn't coming out with the right percentage. I'm doing something wrong there, but I don't know what it is. Or sharing the screen again. Or here's another example. So that's a really cool example. I guess for now, maybe I'll go back and change this in the notes later on, but this was supposed to be 0.48. Check. Sure enough, it came out 0.48. That's cool. It worked. Let's look at a kind of a limit example. You remember that that's kind of what calculus evolved to, but we had statements like this that came up as a part of calculus. And we asked, what is the limit of that as x? We always wanted it to be the one thing it can't be. So what is that? Well, unfortunately, when you stick 0 into that, e to the 0 is 1, you get 1 minus 1 on the top, which is 0, and on the bottom you get 0 over 0. And so I can't put 0 in, but this is saying something different. Despite the fact that that explodes at 0, the limit of that does not approach 0. And again, you're more than welcome just to do the easy thing with the calculators you have and stick in 0.001 or something like that, and you can probably see it's approaching something. But now that we have the ability to replace, so this is really cool, watch this. Now that we have the ability to replace these crazy statements with other things, didn't we just say that e to the x was 1 plus x squared over 2 plus x cubed over 3 factorial, or x cubed over 6 plus x to the 4th over 4 factorial, x to the 4th over 24. Well, do you see what happens to that expression if you do that? So notice you end up with 1 minus 1, like this minus 1 and that one go away. And so on the top, you have now x plus, I guess I could just copy that. So the ones cancel out. You have all of this on top, and you have an x on the bottom. And so remember back when we were studying slopes and so forth, the problem with this 0 was the fact that there's an x on the bottom, and that's what's making this 0. Well, notice you can actually simplify that equation now. Like every term on the top has an x in it. So that means one of those cancels out. And so you end up with, well, x divided by x is 1, and then 1/2 x, and then 1/6 x squared, and then 1/24 x cubed. Do you see why I don't need to keep going here? Does it make sense? It is now okay. The prohibition against entering 0 for x has been lifted. You're free to put 0 in for x now where we weren't before. And so, oh, look, all these terms just go to 0. So look, I don't really need to write them. So apparently the answer to this is 1. So you could verify that on your calculator. You could go get your calculator, put 0.0001 in for x, and you'll see it's actually approaching 1. It actually doesn't explode. You can't put 0 in, but it approaches the limit of 1. And that's, you know, a lot of what we've been discussing this entire time in calculus. It's what calculus is all about. So we're doing right now, where we're saying, hey, this equation, e to the x, is equal to this other equation. Well, it gets really close to it if we have more and more and more and more terms. It approaches a limit of that as long as we have this dot, dot, dot on the end of it saying it doesn't quit. Just like right here, we're saying dot, dot, dot. We get really close to 0. We actually get to 0. Well, if you actually get to 0, it doesn't explode. It's 1. And this ability to replace one function with another function that's way easier to work with, that's the payoff of all of this. Does that make sense? Or again, interrupt with thoughts and questions as you see fit. Or this, let's look at kind of a trig example. like if I asked you to take the integral of not the sine of x, unfortunately, but the sine of x cubed. This is very much like what we just did with e. It wasn't just e to the x, it was e to the x squared, and that's really damaging. And this is no different. I'll quickly do this just for your thinking. We know the integral of sine is negative cosine, since the derivative of negative cosine is sine. But what about that x cubed? That's the problem. In other words, if you said, well, I'll get rid of it. I'll let u be equal to x cubed, which means du equals 3x squared dx. So then I can replace this with just the sine of u. Cool. But then dx ends up getting replaced with du over 3x squared. And so bummer, I'm not happy there's still an x there. Does that make sense? So this problem would have been possible if there happened to be an x squared in front of it. It suddenly would have got easier because then it would have canceled with that x squared. But how are you going to get rid of that x squared? Well, I guess you'd have to resolve this equation right here. You'd have to resolve that for x squared, which you could do by raising both sides to the 2/3 power. So there's x squared. So, okay, great. We did it. We replaced it. So now it's times 3 times divided by 3. I guess I'll just write it down here. 3 times u to the 2/3 power du. We have successfully got it into u world, but do you realize, like, you still can't do it? It's worse now, actually, because that's like quotient rule. And so we'd have to try integration by parts. And so this is difficult, if not impossible. Difficult, but if not impossible. Why am I showing it to you now? What are we going to do with it? We are going to take the fact that sine of x can be replaced with a polynomial. But notice it's not just sine of x, it's sine of, well, junk. Like, it's not sine of x, it's sine of x cubed. And so does it make sense? I'm going to have to replace this with x cubed, that x with x cubed. So it'll be cubed cubed, it'll be to the 9th, and that'll be x cubed to the 5th. But it's a polynomial. Like, it'll be easy to take the integral of this because it'll be a polynomial. You see the power of this? So since, whoa. Since on the note sheet, and again, this will be part of your test, I'll tell you on the questions, I want you to do this by hand. Does it make sense you could do this by hand? You'd have to find the derivative of this and the derivative of the derivative and the derivative of the derivative of the derivative. And we could make the Taylor series expansion for this ourselves. But if we're allowed to, hey, we already made this once before, let's not make it again. So the note sheet says that sine of x is equal to 1, or just x, minus x cubed over 3 factorial. I guess I'll leave it as factorial right now, plus x to the 5th over 5 factorial. Again, notice that's a recognizable pattern. I can totally tell what's coming next. That's kind of neat that it's that simple, if you will. So I'm just going to replace this. I'm going to make a new series out of this. So for us, then, this problem would become, well, what would it be the integral of? Well, not, so it's x, and then minus x cubed over 3 factorial, and then plus x to the 5th over 5 factorial. What changes? Nothing, just that our x is an x cubed. That's the only difference. Maybe I'll write out one more term just for the fun of it, since it's so easy to see what the pattern is. So the key here is, because of this dot, 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 we are going to approximate the answer to this. We can't find the exact answer because dot, dot, dot means it never ends. So to write it out a little more clearly, I guess it'd be x cubed minus 1/6 x to the 9th plus 1 over 120 x to the exponents, x to the 3rd to the 5th. You multiply exponents. In that case, that becomes to the 15th. And then minus, I don't know what 7 factorial is, but I can find it. It is 5040. So this is 1 over 5040 x to the 21st. Let's see, is there a pattern there? Yeah, plus 6, plus 6, plus 6. So I could actually do the next one because I know it's going to be 6 higher. That's kind of cool. Now, to the point of what we did back in chapter 10, do you agree that this thing is on its way? It's definitely converging to something because of this term right here. Like, look what that's doing. I mean, whatever x to the 21st is, 1 over 5040 is making it go away quickly. Now you might think, well, x to the 21st, what if you put in like a 9? Isn't 9 to the 21st a huge number? Yeah. Remember, what you have is you have a power equation on top competing with a factorial on the bottom. Who wins that? The factorial wins. So this is on its way to 0. This will converge to something. So anyway, that's just kind of a blast from the past. But so there we have an approximation for this. We have 4 terms. This is P4, I guess you could say. So I could sort of add that. I would have to do that on a test, right? I would have to say use P4. And then secondly, I'd have to, like, if we're going to approximate this, we have to, have some numbers to actually use for this, right? So let's see, where does sine exist? Let's do this let's do this so I can put it in the notes. Let's take a look at the graph, since I'm just making this up, and I like to make these things up kind of live because I think it helps you understand a little bit more. But let's go in here and say f of x. Let's graph the original graph. That equals the sine. I think I can just go find it faster. Not tangent. Come on, man. Hit the right button. Sine x raised to the 3rd. Get out of there, close the parentheses. So I'm trying to find the area under that graph. Isn't that a fun graph? So I just want to pick something that comes out kind of nice. Remember, the area under the curve below the x-axis is negative. I don't know. Let's go 0 to 2. So they'll be positive on top and negative on the bottom. So I could go over here and say integral from, let's just make sure this kind of comes out as like some reasonable answer. So f of x, and we have to say, if you didn't do Desmos, from you that came from the other campus, you got to put the dx in there, which is kind of cool, or it won't tell you the answer. So the area under that curve is a total of 0.45. And so remember, we got some positive and some negative there to produce that. And so again, it's in the real world, you can cheat thanks to the technology that you and I have. We don't really need to do what we're doing right now, right? Like I don't need 11.4. I don't need infinite series and so forth to approximate this. But people in history did before us. If I want an approximation, there you go. I'm done. Got the answer. Thanks, technology. That's really cool. Or Simpson's rule would have done the same thing. Let's see if we can get that same answer using our technique. So I will snap a pic of this. The only thing Desmos doesn't do that your calculator does that I think is kind of cool is it actually draws a picture of all those areas. That'd be kind of neat to see that, I think. I'd like to see that area. So awesome, we have the right answer. You get a step ahead of me. I'll clean this up a little bit. I'll crop this up so it looks good. You get a step ahead and try to figure this out yourself. So we have that positive area, that negative area. This is positive, this is negative, this is positive. And the net result is 0.452 approximately. Let's see if we can get the same answer. If we also go from 0 to 2, catching up to you now. So the integral of x cubed would be 1/4 x to the 4th. X to the 9th would grow to x to the 10th. When I divide by 10, I get 1/60. And x to the 15th would grow to x to the 16th. And 120 then would be multiplied by 16, which is a big number, 1920. Notice I'm putting, well, fairly decent sized numbers in here. Like 2 is a pretty big number. 2 to the 16th, that's a huge number. This might have a lot of error. I kind of hope it does, just so that you kind of realize there's the concept of error is pretty important. So the x to the 21 would grow to the 22, 50, 40 times 22. 110,000, 880. And so now I can evaluate that at 2 and at 0. And of course, I'm very happy I picked 0 now. I didn't think about it at the time, but I don't have to do anything for 0. So all I have to do is stick 2 into that mess. But again, 2 to the 22nd is a big number. I'm guessing this is going to be a terrible estimate. Like it needs to be kind of much more accurate than what we're really saying here. So 0.25 times 2 raised to the 4th. Should just be doing this in Desmos. Minus 2 raised to the 10th divided by 60 plus 2 raised to the 16th divided by 1920. I'm guessing this is going to be massively off. 2 to the 22nd is a huge number. This might need to go further so that we actually see the exponential winning. Yeah, I got negative 16 for that. It's not even close.
That's what I got when I put it into Desmos.
So do you understand the concept of why that's happening there? Because the number on the bottom isn't growing fast enough. Like we need some more terms. So again, I find myself wanting to go look at Desmos and again, wouldn't it be nice to use the sigma notation in Desmos? Like, would we be capable of writing a formula for this in Desmos? Could we write a sigma notation for this and see if it would actually produce the same answer if we had more terms to it? I'm thinking out loud to myself right now to see, would we be able to do that? Let's see, where did all this come from? Let's think about sigma for a second. This is fun to play. So we needed to take the area of this. Yeah, that's not hard because this was just 3 factorial and that was just 5 factorial and this was just 7 factorial. The question is, could you write an n formula that would produce when n is 0, it would produce that. When n is 1, it would produce 9. When n is 2, it would produce 15. When n is 3, it would produce 21. Can you write a formula for that? It's not just going to be like 2n plus 1. Notice it's, as I said before, plus 6, plus 6, plus 6. If you repeatedly add 6, what is that? Let's try it. I'm a little worried about going over here because I'm afraid I need to copy, but let's try this. So if we say g of x is equal to, and we bust out the sigma notation, and we say from 0 to, I don't know, say 4 for now, then what did we just have? Well, we had, did it alternate? It did alternate, didn't it? It was like plus, minus, wasn't it? So let's see, is it then -1 raised to the n power, and then that was always divided by n factorial. Uh-oh, factorial. Do they have a factorial in here? Anybody see factorial? Stats. It's going to be in stats. It's in here.
Does it not work to just type an exclamation mark? Or
That's what I'm looking. That's what I'm looking for. If I
I think it's at the bottom.
There it
You
is.
see it on the bottom row.
Thank you. And then it was X. Anybody succeed with the formula for that? If you repeatedly add 6, we need it to produce 3 and then 9 and then 15. What would the formula for our exponent be?
I think it would be 6n. Yeah.
Exactly right. If you're repeatedly adding 6, repeated addition is multiplication. So it'd be 6n. Except for we need 3 and then 9 and then 15. So now how do I modify that? How do I modify that? Well, if I put 0 in, 6 times 0 is 0. Well, then I'm going to get 3. Then as if I add 3 to it. Does that work for this one? Yes, we put 1 in. 6 times 1 is 6 plus 3 is 9. 6n plus 3 is our formula for that n up there. Isn't that kind of cool? Again, we're just playing. This is, where am I? Oh yeah, over here. So that's actually 6n plus 3. If I remember right, I have to put this in parentheses or it isn't going to like it. So let's do it. Parentheses 6 times n plus 3. Notice it's not working yet because it didn't match the graph, right? It's supposed to be the same graph. Well, yeah, it is working. It's not the same graph everywhere. Notice it's the same right around 0. But I only have 3 terms. So
do we need to have 2n plus 1 where the n is? At the
we
bottom?
might, yeah, we might. You mean for the n factorial?
Yeah.
I don't think so, because didn't that just, oh, there was a little more to that, wasn't there? I wonder if we're playing with this a little too long. I'm looking at this and wasn't it just, oh yeah, 2n plus 1, because it was 1 factorial, so it would be 2n plus 1, Ben's right. So that's a little more complicated. Ah, there we go. That's even better. It's a better match. And we must have got lucky on -1 to the n because I didn't play with that yet. Does it need to be n? Does it need to be n plus 1? That our first term was positive and -1 to the 0 would make positive. So that's right. So notice it's matching, and so let's go back and, throw a larger number in there instead of 4. Come on, let me have that. Backspace 8. Do you see the problem here? We went from 0 to 2, right? And we didn't have this many terms. How many terms did we have? I forgot. We went out to n is 3. That's all the further we went is to n is 3. Does that make sense? That's not good. That's why this happened. So if I back this up, it was even worse than what I had a second ago then. So if we only go backspace 3, does it make sense the area under our green curve from 0 to 2 would be a big negative number? So it wasn't accurate enough. Do you see why error is important? So that's why our answer is terrible. We needed more terms, and so there wasn't another mistake. So, again, if I just play with this a little bit, which is all I'm going to do right now, we saw 8 was getting close. Let's take it out to like 20. Does it make sense that's too many? You don't need that many. That's the exact match from 0 to 2, isn't it? So I don't need 20 terms. I could get away with less. What about 12? Yep, 12 looks pretty good, doesn't it? What about 10? Oop, not 110. What about 10? Okay, I could live with 10. Now remember though, we just did 3. This is a lot more terms. Like this would take a lot more time. But that's kind of cool to see, isn't it?
So what's wrong on ours?
We don't have enough terms. We did this with a graph that looked like this. We found the area under that green curve from 0 to 2. Well, notice it goes down, 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 down forever. Like we're getting all that area over there negative. That's why we got negative 16. So we didn't do anything wrong. We just didn't have enough terms. Again, I partially apologize for my teaching style, because as you can tell, there's many things like this where I just start playing. Like this is what true mathematics is. We're playing, and I didn't think about this ahead of time. I didn't know this would happen. I didn't have any terms, but I think you learn more from that. I mean, it creates some inefficiencies, and that's the part I apologize for. But I think in this case, paid off for us, because we can see why this happened. So let me just kind of write that in the notes. Is everybody seeing it? Do you see why we got the answer we got? So it actually wasn't wrong. One possibility was, well, we made a mistake. I made a mistake, but no wonder we got 16, because our area, switch to blue, the area we got actually was this, right? Notice that just keeps going down. So no wonder we got negative 16.7 for the area. So too few terms, question mark? The answer is yes, too few terms. That's kind of cool. Okay, so I got to show you something now that is spectacular and just out of interest. Actually, maybe this is a good time to talk about error. Let's talk about error. I'm going to make this kind of brief. This is actually something that you need to know for one question in 11.3, but this is why error is important. And I think you're in a position now to understand that. So I'm just going to tell you from 11.3 kind of quickly what the Taylor remainder theorem Taylor remainder theorem is. It basically says this, and remainder is abbreviated as it was in previous sections, RN for remainder. And then we're going to do a quick example of kind of how this works. So here's what it is. The absolute value of that remainder for some particular number. Now notice we just did a problem where we were trying to figure out, you know, how close of a match was this, and we did it for, well, n was 3, right? We chose 3. So for some x value, that remainder will be less than the maximum of the derivative. This is going to sound confusing, I'm sure, of one more than that. In other words, we went to the third term just now, but you go one past that to the fourth term. You take the fourth derivative, evaluate it at some number c. It's going to be very confusing until I show you an example. So if you are confused, do not be surprised. The maximum number we can possibly find for that statement right there, multiplied by the difference between, I'm just going to write it out. If I try to explain it now, it's just going to go nowhere. So the important thing to notice is just we're looking at the next term after it. In other words, if we stopped at n is 3, then this is all about 4, the fourth term. Now, this part shouldn't look totally new because this was the remainder formula for an alternating series. You basically just took a look at the next term. And what is the C value? Well, remember that A was the number you centered it at, and X is the number that you're choosing to look at. And the C is somewhere between those two. Now that should make no sense to you at all. Like, I don't even know what you're talking about, is what you should be thinking right now. Let's do an example. So consider this problem from 11.3, and you have a problem in your assignment kind of like this. So that's one of the reasons I wanted to get to it. So let's make a model for that at x equals 6. So we're centering it at x equals 6. So that's really kind of our A value. Maybe I should even just write it that way. It's kind of like your A value is at 6. Now, this is not one on your cheat sheet. Like, this isn't one of the classic common expansions. And so we got to make this ourselves. So let's go take some derivatives and so forth and figure out the Taylor series approximation for this. So this is our f of x formula. So what do we need? Well, we need to know what f of, well, 6 is. If I put 6 in there, and I chose this all to work out kind of nice for us. 3 times 6 is 18, minus 2 is 16. And fortunately, 16, and you may remember that 4 down there is the 4th root of 16. Well, that comes out 2. That comes out nice. And so then you have 2 to the 5th. And so this actually comes out 32. So there's our first coefficient. This is also good prep for the test because you got to be able to do this. Then I need the derivative. Okay, I can take the derivative of that. I can find the derivative of f of x. Let's see, it's just power rule. So the 5/4 comes down front. The junk inside stays unchanged. I take 1 away from 5/4. 5/4 minus 4/4 is 1/4. And then chain rule says I have to also multiply by 3. So let's see, I guess that's 15/4 then, just to write it a little more cleanly. And so then what is f prime evaluated at 6? Well, again, 3x minus 2 with the 6 in there is going to be 16 every time. The 4th root of that is 2, and then 2 times 15 is 30. So you have 30 over 4, or 15 over 2. So there's our second coefficient. So I'm just trying to find all the coefficients that we need. So that we get everything we need. Okay, so let's do kind of one more. Let's stop at the second derivative because we decided we're tired. And so, okay, I'm taking the derivative now of this over here because there's the first derivative. So 1/4 gets multiplied by 15/4, so that'd be 15/6. The junk inside stays unchanged, and then I take 1 away from 1/4. 1/4 minus 4/4 is actually -3/4, and then I still have to multiply by 3. So I guess that's 45/6 times 3x minus 2 to the -3/4 power. So what is my coefficient then at 6 for that term? So that I can add a squared equation to this. In the interest of time, 45 over 128. So I have the original, I have the first derivative, the second derivative, so I have everything I need now to write a Taylor series approximation that has 3 terms. So it'll be a second degree polynomial. So what did Taylor series say? It said, take that expression, your first coefficient is your first answer, and then it is your second coefficient, 15 over 2, divided by 1 factorial, but 1 factorial is just 1, times x minus 6. Since our a value is 6, that's to the first power. So remember, there's really a 1 factorial here, there's a 0 factorial here, and there's actually an x minus 6 to the 0 power there. It's just that this is 1 and this is 1, and that's why all that stuff kind of simplifies a little bit, just to make it look a little cleaner. And then my next term, it's 45 over 128 times x minus 6 to the second power. And so I have a squared equation. Now I'm missing one thing. Did anybody catch what I missed?
Have to divide by 2 factorial.
That's exactly right. This coefficient has to be divided by 2 factorial. So since 2 factorial is 2, and I think rather than entirely erase it, I'm just going to cross that out and say 256 since I'm dividing by 2 factorial. So there's a squared equation that models our equation, right?
Doug, I just have a quick question. So for the second derivative that you have,
Mhm.
how did you get 15 over 6? Because I got 15 over 16.
I meant 16. I said 16. I did not write 16. Thank you for catching that, because that would have made us get this wrong. And you saved us. Fortunately, I looked over at my note sheet because I did prep this one ahead of time, and my 45 over 128 is actually right, because so when I plug 6 into this, I end up with 45 over 16 times 2 raised to the -3/4. And that turns out to be 45 over 128. So thank you for catching that. I don't think there's any more mistakes. So we'll be prepping for the test tomorrow, but armed with, this formula here on the note sheet, can you do that for any equation now? I mean, I need to be staring at that, right? Because otherwise I might forget the 2 factorial and the 3 factorial and all that. So my a was 6. So there was my 32 right there. And then my derivative evaluated at 6. And then my second derivative evaluated at 6. And the powers of my x minus 6 just go up from 1 to 2 to 3 to 4. So we'll practice that some more tomorrow, but I'm just taking advantage of that, doing it kind of quickly. And so I could get great. I got this polynomial here now. So the question is how does it compare to the original? Like, how close are these? Is P3, we would say P3 is an approximation for f of x, right? So what if you wanted to use this for something? Now, as I said, f of 6 was easy to find, right? But can you appreciate some ancient person wanting to know what would happen if I stuck 4 into that? Well, notice 4 times 3 is 12 minus 2 is 10. Does it make sense that now you are tasked with figuring out what the 4th root of 10 is? So everybody except for the last 40 years of us didn't have a calculator. So they don't know. You see what I'm saying? They don't know the answer to that question. Now they did know the answer to 6, right? Because the 4th root of 6 is 2. It comes out a whole number. So 6 worked great. So they're stuck. They need an approximation for 4. So we say, hey, I can do that. I'll just come down here and I'll stick 4 into my equation instead. You understand the logic in that? And notice that can be done with just regular add, subtract, multiply, and divide. Now, to save some time, I'm going to stick that in the calculator so that, you know, we don't sit here all day. So 7.5 times 4 minus 6 would be -2 plus 45 divided by 256 times -2 squared, which would be times 4. I got 17.7. Somebody double check me. As you've seen, I make mistakes. But I think I put 4 into that. No, yeah, that's right. 4 into that. And that's what I think I got. So there's an approximation. Now, the concept of error. One of your assignment questions says, what's the exact error? Well, we have a calculator, so we can actually find the exact error, right? Like we know what f of 4 actually is. Well, let's do that. The original problem was 3 times 4 equals 10 to the 5/4 power. So my calculator will tell me what that is. 10 raised to the 5/4 power is 17.78. Notice that's a pretty good approximation, right? Like it's working. And I kind of wimped out and only made it to a polynomial, and it was close. Now, again, why did that work? Well, because I chose 4, which is reasonably close to 6. Does it make sense? If you choose a number that's a long ways from 6, like 23, it's probably going to be a terrible approximation, right? We'd have to look at the 2 graphs and see if I compared P3, if I compared these 2 graphs right here, I'd be able to tell, you know, are those reasonable? But remember, ancient people don't have graphing calculators. They can't graph stuff. They never saw a graph of any of the things we've been graphing. That's very hard to make a graph of something because you have to find a bunch of answers, and you can't find any answers because you don't have a calculator. So we can actually get the exact error here by just subtracting those two. 17.783 minus 17.703. What is that? 8.08. We can find the error because we can cheat and know the right answer. They couldn't do that. They don't know what the error is. And so, you know, what's the error? Well, let's try to use this ridiculous statement up here now and make an approximation for this. Because right now, as I said, you probably have no idea what that was even talking about. So what's the approximate error of this? Well, what does all this mean? Well, some of this makes sense. In other words, okay, well, we have x minus 6, except for we're going 1 higher power than we went, right? That's what that's saying. What did we do? We went to n is 2. Is that right? 0, 1, 2. Yeah, we went to n is 2. So we'd be going to 3. The next term, x minus 6 cubed, and divided by n plus 1 factorial. So since n was 2, 2 plus 1 is 3, that'd be over 3 factorial. And so what we're trying to find then is the error in the fact that we chose 2 n is 2. And we chose our estimate to be 4. Does it make sense? That's what our x is. We said we're going to estimate 4 with a 2-term polynomial, or an n equals 2 polynomial. Again, notice the confusion, like, because I find this confusing. Like, we chose n to be 2 and it created 3 terms. Does that make sense? So, you know, what do I call this thing that I made? Do I call it a degree 2 polynomial? So it's 2, is that P2? Or do I say it's P3 because it's n is 2, which created 3 terms? And so you see what I'm saying? Like that's kind of confusing, or you could sort of mix that up. What is that really saying? So in this language, they said, well, that's n right there. Okay, so part of this makes sense. I'm going to come back here and throw 4 in here, because our estimate was based on 4. This is what we were trying to estimate. It's 4, x equals 4. And so what is this max business? What's this f of n? Well, we got to take the next derivative. So what is f n plus 1? Notice it's in parentheses. It doesn't mean an exponent. It means the derivative of that. And then we're going to evaluate it at some c value. Okay, well, what's our next derivative? Well, we had our derivative back here. So do you agree I got to take the derivative of this? This was our second derivative. So we need the next derivative. Well, that means the negative 3/4 would come down front. So 45 would get multiplied by 3. What is that, 135? And it's multiplied by a negative. And then 4 would get multiplied by 16. So that'd be 64. And then it'd go down to 3x minus 2. We'd subtract 1 from it, which would make that now negative 7/4. We'd still have to multiply by 3. So there's our derivative. I guess I'll go ahead and multiply that out. 135 times 3, 405. So we get negative 405 over 64 times 3x minus 2 to the negative 7/4. And so what's the c? What's the c we're plugging in? Well, as I said before, that didn't make a whole lot of sense. C, where did you go? This is what c is right there. It's somewhere between a and x. Well, now that makes a little bit of sense, a little bit more sense. So c is somewhere between a and x. Well, our x was 4 and our a was 6. So we're somewhere between 4 and 6. In other words, what we need is for this to yield the max number between 4 and 6. So, you know, is it 4? Is it 5? Is it 6? We got to find the biggest number possible. Remember, this formula says the error is less than this. So we're trying to just make sure we're safe. We got to be sure. So we just need to take this expression then and put 6 in there. Like, I got to change colors. We got too many reds here. You do this. Try 4 in here, and also try 6 in there. Or you could graph it. You could actually graph that and see, like, where's the biggest answer? That'd probably be safer. My guess is it's one or the other, 4 or 6, just to save time. So I'm just going to type that in. Negative 405 divided by 64 times 3 times 4 minus 2, all raised to the negative 7/4 power. So when I tried f of 3, the third derivative, evaluated at 4, I got negative 0.1125. When I tried 6 in that derivative, I got negative 0.049. So this one's bigger. So just pick the largest one. That's what it's saying. So now I have everything I need. So I can say, what is our second degree polynomial evaluated at 4? What kind of error can I expect? Well, it's going to be less than my large answer here, 0.1125, multiplied by this expression here, 4 minus 6 absolute value raised to the third over 3 factorial. There's my error. My error is going to be less than that amount, whatever that is. So I'm going to type that in. Negative 0.1125 times negative 2 raised to the third power divided by 6, which is 3 factorial. I got 0.15. So my error is less than 0.15. Now, how much less? Well, they don't know. They have no way of knowing. That's not something I'm going to ask on a test. Which is nice of me. I could. But it's just because we haven't talked about it that much, and it's kind of a crazy process. But I think from what I just showed you, do you see how important this is? Like logically, if you actually are doing this for a reason, we just missed one of our problems by a mile. And so we would need to know, oh man, that's going to be a huge error. Okay, well then go add more terms. Don't do this for 2, do it for more terms. Notice our answer, the actual error was 0.08, and we said we're guaranteed it's going to be less than 0.15. Well, it is. We don't know how much less. Well, we do, but they didn't. But isn't that kind of cool to say? I mean, if I was doing this in ancient times and I realized, oh, you mean I can only do this? You mean I can do this for only 2 terms? Like I can get a squared equation to model this, and I'm only going to be off by 0.15. Close enough for me. You know, if I'm trying to build a bridge or whatever, that's close enough for the value of 4 plugged into that. It's close enough. That's great. I can live with that. Cool. Let's just have 2 terms. So I do want you to understand this conceptually. I think it's kind of powerful that you do so.
Hey Doug, real quick, I missed where we got the 4, like x equals 4.
I just picked it. In other words, clear back at the start, this was like an ancient person saying, I would like to stick 4 into that.
Oh, okay.
I made it up. In other words, someone says, I'd like to put 4 in there. And then they realize, oh man, I don't have a calculator. Those aren't invented for another 100 years. What am I going to do? Okay, well, I'll rewrite it. I'll rewrite this ridiculous. Remember, this is a rational equation. It's really this, isn't it? It's the 4th root of 3x minus 2 to the 5th power. And if you were to actually multiply out 3x minus 2 to the 5th power, that'd be this gigantic polynomial, be the 4th root of that. That's a terrifying rational function. Does that make sense? And we just replaced it with an equation that's really easy to work with. That's the backbone of all of chapter 11, replacing ugly with something not ugly.
Okay, is there any way that you could like mess that up, or you pick something close to A? Is that what in your mind, or is it just you could literally pick any number for X?
Yeah, and that's where the radius of convergence business comes in. Like, is it okay to put X as anything into this? And I'm picking examples where we're not having to think about that kind of stuff right now. But yeah, and so the key is really the graph. You know, in our case, we can actually graph them, and as we've been doing a little bit, and say, you know, does this look reasonably the same? Is it okay out to there? And again, let's do that really quick. I have one other cool thing I want to show you, but I'll show it to you at the start of tomorrow instead.
We'd say it's centered at 4, right?
Centered at 6.
Or at 6, yeah.
So because I'll be able to do it faster, I'm gonna do it in the regular computer version of this. So we're saying we are interested in the function 3x minus 2 all raised to the 1, didn't that go away? 3x minus 2 raised to the 5/4 power, which we now discover to our excitement looks like this. So, oops, that's not what I want to do. So we say, okay, cool, there it is. And notice again, it looks really like skinny and weird. I'm going to go back and exacerbate its shape a little bit more so we can see it. So that's a little better. So it's kind of like, I don't know, one side of a parabola sort of a looking thing. And so we're saying, hey, I found a model for this. And I'll just type in our squared model that we think we found. Where did it go? There it is. G of x equals 32. And again, let's watch it working. We were interested in this, remember, at the point where x was 6. So I'm going to graph this point for us so we can look at it. 6 f of 6. Oh, way the heck up there. Where are you? 6 f of 6. I didn't say graph it. What's wrong? How come I don't see it?
I think it's up by 32.
Did I just not go high enough? Yeah, it should be at 32, right? No, yeah, there it is. I just never went high enough. Wasn't thinking. So again, our can't have this be the same color. That's not going to work. So our green graph is as good as you can get if all it is a constant. So then we said, okay, let's add a second term to it. And we said that was plus 15/2 times x minus 6. So how come I don't see it?
It's on top of it.
Because it's already darn good. That's exactly right. Look at that. It's got the same slope. It's already pretty good, isn't it? So just for the fun of it, what's f of 4? If we, we saw the actual answer a minute ago, that was the answer. What if we had wimped out and stopped with one less term? Notice that's still off. It's off by 0.78. And so, you decide that's not enough. That's too much error. I don't want to be off by that much. Okay, well, then let's add one more term. We saw that next term, we'll quit right here, was 45/256 times x minus 6, all raised to the second power. Now it's a parabola. So now we were modeling it with a line. Now we're modeling it with a parabola. Notice again how good it looks. Again, where does it look good? Right around 6. How good of a model is it going to be if we plug in, some larger number like 100? Well, it's going to be terrible, right? If we try 100, going to be terrible, too far away. Does that mean it's outside the radius of convergence? No, it just means we need more terms. And so this was our model. We said, okay, cool, let's quit right there. And now we're happy. So these are the same two answers we just got a minute ago. And so notice they do look indeed pretty good. And so that's awesome. I think what we did today, I hope did a good job of, although, we looked at some things that were hard and so forth, that a good job of helping you understand what you're doing with all of this, like what it can be used for, and why error is important and so forth, and having some sense of what that error is and all of that. You can see that there's a lot to consider here. I'm not going to make this test inordinately hard, as long as you can do some of the problems we did at the start of today, cheating and using the note sheet, and as long as you can, as we just did with this problem, make a model yourself, but from scratch. It's kind of the way I'll say it on the test. Make this from scratch. Well, we just did that from scratch. We didn't use a cheat sheet. Well, there wasn't one for this particular problem. So then I think you'll be good. So fortunately, we get tomorrow to kind of look at, again, both the review that I already have posted for you, and also, to practice, but also that's me telling you what's important in this last section. And you'll see there's not remainder problems and so forth on it. I mean, these are neat, but there's not that. I'm not going to give you sigma stuff. I'd probably make everybody's grade go down at least one grade if I added those things in there, which I could do. but I don't want you to miss the cool part of this. I could stress you out and make this class horrible really easy by emphasizing all these little details rather than letting you see the beauty of it. And so that's my error as a teacher. And fortunately for you, that's going to make your grade a little better, I think. All right. 926, that's not too bad. I think we're done. Stay after or bail.
So is there a radius of convergence to this? Because from what I understood last week, the radius of convergence could be found by that 1/1 minus x expression, and we didn't want that to be 0. But like something like the one we just did isn't really divided by anything. So
Yeah, so let's consider that just for whoever wants to stay after. So let me just show you one thing. In these power series expansions, notice this top one up here. Let me get rid of all this junk on here so you don't get confused. Notice this top one up here says it's only good for x's that are less than 1. I'm not sharing a screen. Why don't you guys tell me that, sir? Cheyenne's just laughing. Come on, man.
I would have told you eventually.
So this top expression, 1/1 minus x, that only converged to something. And again, you can see it right here totally. Like, doesn't that x value have to be less than 1? I mean, if you're squaring it and cubing it, it's just going to get huge if it's more than 1. So that series is not going to add up to something unless x is less than 1. And so that's pretty small. In other words, we can't use this anything outside of 1. But notice lots of the rest of these, anything you want for E. You can pick any number you want. Sine and cosine, pick anything you want. Awesome, I like those. Natural log, not so good. Got to stay between 1 and -1 again. Oh yeah, same thing for this one and same thing for that one. And so that's the idea. Well, what's ours? Ours isn't on this list. And so, how do we figure this out for us? Well, if it looks like this, the number that's here being raised to a power, that number's got to be less than 1. So the question is, does that work for ours? What number is sitting there? Well, it's 3x minus 2, isn't it? Is that right? Wait, was that a derivative? There it is. It's this is our expression. Does it make sense that as I watch this cruising out there, well, one possibility is there's two things happening here, and this is the larger issue would take more time and makes it confusing is kind of like one thing is x minus 6 better be less than 1. Does that make sense? Because if I'm going to be squaring it and cubing it and all that, that expression better be less than 1. Well, wait, it wasn't less than 1 for us, right? Didn't we put in 4? 4 minus 6 is -2. Like, we chose a number that was outside that. So, what's going on? Well, one is that expression, but the second thing is, what about this coefficient? Remember what we said is if that number down there had a factorial in it, factorial might outrace that. So even if this number was, as we saw, 2 to the 16th and, so forth, it got huge in that one problem that we did, maybe the coefficient will cause it to go away as well. So what's the test in this case? I only showed you one example of this, but this is where the ratio test comes in. We can actually find it. In other words, it will converge as long as the limit of the next term divided by the previous term approaches a limit. And that limit is less than 1, which basically means the next term is smaller than the term before it. Does that make sense? If a small number is divided by a big number, then you get a number less than 1. So we could find the radius of convergence of this. And again, this is the kind of thing that would make you go from an A to probably a C in this class if we emphasize this. If I said, what's the radius of convergence of this? And I didn't think they did that good of a job in the text of 11.2. That's what 11.2's topic was. But if we were going to talk about radius of convergence, it shouldn't have been back then when you didn't even understand what it was for. It should be now that you can see it modeling things. Now, if we talk about it, it would kind of make some sense. So the problem with this is we've got to, because in my case, I don't know, like, you know, I haven't thought about it yet. You're just asking me this question live, so I didn't think about it. You know, did our bottom number have a factorial in it? I don't remember. Yeah, it did, right? Because this was, yeah, they all do. Like this was 1 factorial and that was 2 factorial and, you know, had other numbers in it as well. But eventually the factorials on the bottom, when you get out there far enough, are going to outrace it. So I think this is going to converge no matter what. But if you will, what's kind of the proof of this? Well, the problem with this is I'm going to have to write a sigma notation for it. That's the problem. Am I smart enough to do that? Am I smart enough to write that down here?
So practically, can we think that the radius of convergence is infinity because we always have a factorial on the bottom? It keeps on increasing.
That's right. In our problem, we know the factorial is going to outrace, and so this is gonna. I think we can be pretty sure, as long as factorial is involved, that it's going to be okay. Let me think about this for a second. And again, I'm jumping off the rails. Let's see. Yeah, you see how this had no factorial in it? This is what Ben's hypothesis is. That had no factorial in it, and so we were sort of in danger of it not converging to something. But sine, look at all these that had infinity for them. Every one of those has factorials in it, and the factorials are going to outdo the exponents. And you can see that happening right here, right? Like x squared is a big number. If I put in 5 for x, 5 squared, 25, that's a big number. 2 factorial, not that big. But by the time you get way out here, pretty soon, no matter what, that's going to converge because factorial's on the bottom. And so it ends up not mattering. Like you can put anything you want. And so as a generality, I think that's exactly right. The proof of that would be in the ratio test. So since the coefficient has a factorial in it, I should even say in denominator. Which, wait a second, didn't all the Taylor series expansions have factorials in them? So the lion's share of the time, they all converge. If you have infinitely many terms, they're all going to converge. But the proof of that would be us writing this statement, kind of rewriting this statement up here, writing that in sigma form, and then evaluating, a to the n plus 1 over a to the n, and seeing if that went to something less than 1. And if it did, then we could say it will converge. We could sort of prove it. Does that make sense? Or verify it, guarantee it. And it would be those factorials in this problem. That'd be the factorials that are going to bring that about.
Yeah, that makes sense.
So let's see, I'm just going to play with this for a second. Feel free to bail if you want to, but I know this part's right. Do you agree with that? x minus 6 to the n, because the first one was x minus 6 to the 0. This one was x minus 6 to the first and then to the second. So I know that part's right. And then where did those coefficients come from? Notice they're really confusing. They're like hard to, this is the part about this that's really hard. It's like 32. I need 32 for the first coefficient, and then I need 15 over 2, and then I need 45 over 256. Oh boy, this is going to get rough right about now. On a side note, I am wondering, so when n is 0, I need a coefficient of 32. When n is 1, I need a coefficient of 15 over 2. When n is 2, I need a coefficient of 45 over 256. I'm wondering, you know, like, how do I find a formula for that? Could I cheat and use regression to find that? We did happen to find the third one, which was negative 405. That's not good. Negative 405 over 64. What's not good about that? All of a sudden it's negative. Like we didn't have a negative problem. Now all of a sudden we got a negative. So it's even worse. And crazily, it actually starts to alternate after that, because I played with this a little bit. So I'm staring at derivatives right now. No, this isn't the right one. I didn't write the right thing down. 45 over 256. I was looking at the derivatives. This number is actually 49,152, and this number over here is actually 1,258,000. It's actually not even million. It's 12,582,912. But they actually start alternating after that. And so, man, how am I going to write a formula for that? This is going to be a problem. Does that make sense? And that's the most important part of this, because that question mark is where the factorials are, and the factorials are where they're going to prove this actually approaches something less than 1. And so I can't just say, oh man, I won't do it. Does that hurt your brain?
Yeah, just the rewriting stuff in Sigma form in general is definitely one of the hardest parts about this.
Yeah, I would 100% agree with that.